please come to the office and pick up your prize. Morgan Taylor, Walker Dreyfus, DeCorian Thomas, and Matthew Cockrell. Congratulations to these 4 students. Thank you.
Come on, you all know that when you have our homework out, we need to be checking out.
It's
Log
definitely
into our computer.
The other one I didn't do is, I think that's 3. I don't know what that is, it looks like 3, so I gotta do that. But
Yeah, he does.
I did that, I got that wrong, and then,
Go and look at your homework, see if you have any questions, want to get your checks.
and I got that one right, I know I got that one right.
The letter?
Okay, well, I didn't.
Yeah, right or wrong?
Bro,
Nice.
bro, try, bro.
Try the homework. You need to start trying your homework, right?
How did you do that?
That's right. You can't be busy enough every single day that you can't even try the homework.
No, the other thing I just didn't have it, and then yesterday I was like,
Where'd you get 36? Why did you add them as well as, whatever?
Don't say whatever, you need to ask questions, sir.
On one question, you talking about number 3?
Yeah, 2 and 3, because I got 2 wrong.
2 and 3, all right, so let's just go ahead and go over these. So when we're multiplying binomials, we need to distribute, right? So we distribute this x to the x plus 3. So you have x times x plus 3, and then you gotta distribute the 8 to the x plus 3. So plus 8 times x plus 3. And then you just distribute from there. And the same process holds for number 3. So we distribute that x to the x minus 4.
Where'd you get the freaking, okay.
Then distribute the 9 to the x minus 4.
We need to
And
ask
then
some questions.
distribute from there.
Oh, okay. Okay, yeah, so I only got a put it on. I didn't put the 11. Yeah, because I know you're supposed to add and multiply.
Yeah. Any other questions?
Oh, yeah, I got one.
Not,
Number 2, how do you get the rate of change?
For which one?
I mean, number 11, my fault.
Number 11? What did you not get?
How do you get a rate of change? I know it's quadratic, but I don't know how to get the rate of change for that.
Alright, so let's start with, so you know it's quadratic, so what type of rate of change does a quadratic function have?
Linear?
A linear rate of change. You can see that when you take these differences, you see that you have -4, -2, plus 0, plus 2, plus 4, plus 6, you know that it's linear, but it's not. We need to then find the constant additive. So you take that second set of differences, and here you have that constant additive. So when you're looking at, so that first set of differences, that is your rate of change. That's that linear rate of change where you see that it's additive, but it's not constant. And then you look at that second set of differences, that's that constant additive. So then that plays into, when we're looking at our recursive equation, we see that when we're looking at that linear rate of change, we make that table separately for that linear rate of change. We can then find the equation from this to then get that 2x.
Okay, I almost messed up on 11 last night because of the +2, but I actually got that right surprisingly.
Nice.
So, that was nice.
Bro, does that make sense, or?
I finally matched the quadratic, because that was one of my problems when we did the thing, so.
Yeah, so just make sure that you identify this quadratic, and then you can make this separate table for the linear rate of change, which will help you make that recursive equation. And then we also always have to have a starting point, but it could be any of these points technically. We just chose either the top one or the y-intercept, but it could be any of the points as a starting point.
My group is over here. It's,
You can switch back to before. Whenever you can do that. Once we start working in groups, you can switch back there.
You can go back right now if you want.
why is my group over here?
Same, dude, same.
Any other questions on these?
Just only the.
It's nice to actually get some questions in this class.
you're number 2.
Here, number 2? Yeah. So, number 2, and I talked to Peyton a little bit about this. So, when we multiply binomials, we want to distribute. So we got to distribute this x to the x plus 3. So that's where we got this. And then we also want to distribute the 8 to the x plus 3, which is where we got plus 8 times x plus 3. So then, from there, we just distribute both of these. So we do x times x, which is where we got x squared, and then x times 3, which is where we got plus 3x. And then same thing for here, 8 times x, plus 8 times 3, which is where we got the 8x plus 24. And then we saw that we could combine these like terms, 3x plus 8x, which is how we got x squared plus 11x equals plus 24. So whenever we're looking at those, multiplying binomials, all we're doing is just distributing. So we got to distribute that x to the x plus 3, distribute the 8 to the x plus 3. Does that make sense?
Yes,
Good. Any other questions?
Bro, you need to be signed in.
I was just listening to him.
Okay, I need you to sign in too.
We can also look at, this was part 2, looking at this systems of equations problem. Do we have any questions on how we did this one? And I would make sure that you at least write down what the answer is, because you will be asked on another part 2 homework to find the solution to this system. So make sure to at least have the correct answer written down.
I think I had mastered that. What was that?
But are there any questions on this one?
Like, what is it? It's just X, Y.
Take it back with you.
You got B?
I gotta get it.
Alright, Carell, what did you say?
What is numbers, bro? Is it like a table or something? I'm asking what it is. I ain't asking like the answer. I'm asking like, is that a table?
What?
What's your number 12? You say X, Y?
Oh, no, this is from a previous problem, I think.
Oh,
This isn't involved.
Yeah,
in
that's
the-
number 11 and 12 that you
Yeah.
just looked at.
Yeah, this picture is just on top of that one. Spade, you said you got B?
Peyton said you got B.
So what's wrong with, why can't it be B?
Oh, okay. No, I read it wrong. That's what it was. Because when I was reading it, it looked like it was saying that he was making $40 for each weekday. And so I matched it with a weekday, but it was supposed to be on the Sunday.
Gotcha. Okay, so yeah, it says, right here it's, earns 25 for each weekday and then 40 each Saturday. So like I said, you just have to read that context to match up how you define your variables with how much it says he earned for whichever situation.
I just read it wrong.
It happens. Any other questions on this before we move into combining linear functions? All right, so if we don't have any more questions, we are going to move ahead and wrap up combining linear functions we're working on. So we'll be ready to take some notes on that, wrap that task up, and then we'll get into 6.4. Ms. Kenny, if you want to go ahead and talk about that task.
Thanks, sir. So you should already have Desmos pulled up. Log in to Desmos. Make sure you put in the code. It is up in the top right hand of the board, right? UJFE4H, getting back to where we were. Also, you definitely need to have out this sheet of paper, because we are now going to finally take notes on the back side where we summarize the things that you have learned. So some of us already made some notes there as you worked through these ideas, but we're going to collectively share out the things that we put into Desmos, and we're going to write it out on the sheet of paper. Shelby, do you want an extra one so that you have space to write?
I'll just erase. This is
You sure?
Can I get an extra one because I was writing on mine?
Because what?
I was writing on mine. Shouldn't have anything. Actually, are we gonna?
I was saying, that's what we're writing on.
Okay,
It's on the back side that we're
Yeah.
writing stuff.
gotcha.
Layla, do you want one? Okay. Desiree, do you need one, or are you good with the amount of space you have? Okay. So, what was the whole point, or the goal, the objectives of the task combining linear functions?
To understand what happens when you use different mathematical procedures to apply it to two different linear functions.
Great, right? So to understand what happens when we combine linear functions through what operations?
The PEMDAS, or the order of operations.
Not through the order of operations, which operations are we using?
Multiplication, division, addition, subtraction.
Right? So we were just adding, subtracting, multiplying, and dividing those linear functions, and we were trying to determine, you said to understand what happens, right? What types of functions did we think we were going to see? Linear, exponential, quadratic, or maybe even None of those, right? I'll leave this here just in case you end up knowing something right on. All right. So what I have done within the slides is I've made a few notes about students that want to share certain ideas. So for instance, yeah, I planned on having Caleb share out, not Caleb, Devin. Caleb was in my previous class. Devin share out about sum of linear functions. Layla's going to get you to add some more details in. So I'm probably going to get Desiree, if you could share some information about sum of linear functions. That means Corel, you're going to add further details down here. Okay. So be aware of where you're coming in. Jalea, you're on the difference of linear functions as well. So come back, internet. All right. So we are starting with the the sum of linear functions. Desiree, what did you learn when we added two different linear functions together? Say it a little louder. Okay, so what changes the slope? By the way, I meant to mention this earlier. Don't forget, you should have typed notes into Desmos. That's why I had you log in. You could go see your notes in Desmos. You weren't here for that? Then I lied. I'm going to come back to you for difference then, because I knew you had notes for that. Corel, do you have notes for sum?
Yes.
Yes?
Sum, yes.
For the sum of linear functions, what notes did you make to yourself?
I put two linear functions. I put it because you add two linear functions, it's going to make a line.
Okay, so when adding two linear functions, that creates a what?
Line.
A line.
Yes, sir.
Thumbs up if you agree with Corel. Thumbs down if you disagree. Agree, 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 agree. Beautiful. So we're all in agreement that when we add, or the sum of two linear functions, that creates a line. Now I do want to point this out. Instead of saying just a line, what type of function would that be? A linear function, right? So when adding two linear functions, that creates a linear function. And so as I said, Layla, I want you to add some more details in on that. Did you discover anything else within your group about adding two linear functions?
Yes, I put the y-intercept. The y-intercept is different.
Y-intercept is different? What notes did you make in Desmos? You should at least have that to draw upon. Huh?
I said it's going slow.
Oh, gotcha. Let's see. Here we go. Here were the notes that I saw you made. Can you read that?
Well,
Okay.
the line makes linear functions. A and C is the slope, and B and C relates to the y-intercept. In my group, all of our y-intercepts are different, but at the end it connects to be the same for A and C.
Okay, and what about this last statement here for
For f of x, g of x, and h of x slopes, we're just adding f of x and g of x slopes to get h of x slope for h of x.
Okay, Shelby, can you reword that or tell us what you think that means?
So for the slope of f of x and g of x, when you add those together, it gets you the slope for h of x.
Okay.
And same thing for the y-intercept.
Peyton, do you agree, disagree, have some other ideas?
I agree with that. Talking about the sum and the difference, both linear or combining linear functions. The thing that I thought about when I saw that was, hey, what makes a linear line, just one linear line? It's the repeated additive property. right? So if you're gonna keep adding to it or keep subtracting from it, you know, because they're inverses, they're gonna keep with that same property that it already has. It's gonna keep with that same identity.
Okay.
So that's not really gonna affect it.
So if you have an
It's
additive rate of change and you keep adding to that additive rate of change or
Right.
subtracting, you're saying that it's still going to be an additive rate of change?
Yeah, because if I want to make a linear line, I could go, you know, and then the slope is up to the right one. If I wanted to keep going downward, I go down to the left one. I mean, it's just literally the inverse. So if you keep adding or you keep subtracting that, it keeps the same property, it keeps the same identity. So it's not really going to make a difference.
Okay, Desiree, what do you think of those ideas that Peyton is sharing? Got nothing to add? You're just like, yeah, that's 100% right? Okay. All right, so one thing I do want to point out, great job on the explanation. Do you need to say linear line?
Linear function, sorry.
Okay, so we could say a line or a linear function. So, but good ideas on that, right? So when we, one of the things we do want to note here is the slope of h of x, right? That's the sum, or the sum function, is the sum of the f of x and g of x slopes. Right? And Peyton's crushing it with this idea that if I take an additive rate of change and I add another additive rate of change to it, I'm just going to increase that additive rate of change, right? Are there any other things that we might be adding when it comes to that sum function? Besides just the slope? Are we adding the y-intercepts as well?
I mean, yeah, you add the y-intercept of f of x, the y-intercept of g of x, you're going to get the y-intercept of h of x.
So same with y-intercepts.
And x.
Hey, by the way, I see a handful of us writing things down, but if I'm writing this on the board and this is a summary of all the ideas that y'all have discovered the last few days, should you be writing this down as well to have as a reference for later?
Yeah, probably.
Yeah, right, like you can always access Desmos to see your personal ideas, but we're not just putting your personal ideas, we're putting the ideas collectively that we all came up with. So we need to have a summary of all this. All right, so Jalea and Desiree, just be aware you are on deck for the difference. All right, Jalea, did you learn anything about the difference of two linear functions? Sorry, let me clarify that. I know you learned things. What did you learn? I know you had to make the note, see what Kelsey said, because your hand, obviously. But come on, let's look here again. Let's remind ourselves, what did we discover, right? F of x is the red linear function. And so now I'm moving it around. And that black function is changing as well. That's the difference of f of x and g of x. But what do you see about that black function, the difference of f of x and g of x? Maybe go back to, was it Corel? Did you give us the information about this information up here? So what did Corel originally say about the sum of two linear functions? I shouldn't say just that creates a linear function. So what happens when we subtract two linear functions? Any idea what it's creating? Say a little bit louder. Julia, what type of function is this red function right here? Say again? How do you know it's linear? How do you know it's a linear function? Just based on the graph, what tells you that's linear? I'm going to come back to you on the purple one. Corel, can you tell us what about this graph tells us f of x, the red function, is linear? It's a line. Right? We got a line there. Julia, what kind of function is this purple function right here? The g of x. The purple one right here. Corel, can you give us your reasoning again on the red one? Julia, I need you to pay attention. Corel, what kind of function was this red one?
Linear.
Why do you know it's linear? Because it's a line. So Julia, what is this purple one? Linear. Why do you know? Because it's a line. So this black function, the difference of those two functions is what? Is it linear? Is that what you asked?
Yes.
That's what you asked? So Julia, is it a line? So is it linear? So the difference of two linear functions is a what kind of function? Julia, what kind of function is the difference? It's a linear. All right, the difference of two linear functions is a linear function. Okay, so Desiree, I think you were here for the differences, right? So did you have any extra notes to make about the difference of two linear functions beyond just, hey, it's a linear function? You didn't add anything else. Did you even look at your notes? Because I know you added other stuff. You're going to make me call you out on lying to the whole class.
No, I didn't have it. I just don't think it's right.
I didn't ask you if you thought it's right. What other notes did you make? You got Layla and Shelby there that you talked with. You're telling me you have you didn't come up with anything or learned anything about the difference of two linear functions. Now I had to show it to the whole world. What you got? What'd you say?
The difference of x and g of x, so on, but subtracting against f of x and g of x, so it's subtracting against the slope of
So thumbs up, thumbs down. Do you agree that we're subtracting the slopes? You agree? Corel, you're agreeing as well? Layla and Shelby. Huh. Why are you scared? You learned it. You explored it. Right? The slope of p of x is the difference in the slopes of f of x and g of x. The only thing I would clarify is I would do the same thing I told Peyton. Do you need to say it's a linear line? You either say it's a linear function
Also, that
or a
goes,
line.
that goes with the y and x intercepts as well.
Does that, let's actually talk about that really quickly. So does that go for the y-intercepts as well?
Yes.
We all saw that? Same with y-intercepts. Now we did not say anything about the x-intercepts before, so let's come back here and look. So I want you to notice, okay, this x-intercept is -3. This x-intercept is, I don't know, about 0.3. And this one is negative 0.8. Can I just add those x-intercepts?
No.
No. Does anyone have an idea why I was able to add the y-intercepts and add the slopes, but I could not do that for the x-intercepts?
And you gotta find a y-intercept, not your x-intercept.
Because the equations we're working with are slope intercept, right? We're adding the y values. So we can add the y-intercepts, not necessarily the x-intercepts. We're going to come back when we look at that in a little bit, but does that make sense, Peyton? So that's a good idea. But I will say this, if you're going to make the claim, hey, the x-intercepts, we just add those as well, you need to justify it. Remember how you tried a bunch of different options with the slopes and the y-intercepts? You should also do that with the x-intercepts. Great idea, but we do want to explore those more, okay? All right. So who did I say for a product? That would be, oh, Kelsey's not here. All right, Peyton, we're going to get you to do product and we're going to get some details from Shelby. Huh?
She carries our class.
I know, she carries our class and she abandoned us. How are we going to survive?
so-
All right. So what you got, Peyton?
I didn't put anything. I'm just playing.
I know that's a lie. I'm going to have
Just
to
fine.
pull yours up like
No,
I
I'm
did to
just
Desiree.
I'm just playing.
All right, what'd you find?
I said that I think it'd be quadratic because the end result has a parabola. Also, I think it's going to be quadratic because it increases and decreases. It has two sets of differences. And I also made a note on the concave up and concave down how I noticed that it changed.
Okay, let's hold on. Let me get stuff written up there because you got a lot that we got to address. Man, that was awesome. Okay, so the product of f of x and g of x is quadratic. Is that what you said?
Yes.
Okay. And why did you say it was quadratic?
Because if you look, it has a parabola.
Okay, because the graph
Or parabola.
is a parabola. Okay, and what else did you say with that?
I also said that it increased and decreased. So
Yeah, remember we did talk about this. Have we studied any other functions yet that both increase and decrease?
no.
No, right? This one does what first?
I ain't decreased my fault.
Then,
Increase.
right? And so we're going to explore those ideas a little bit more heavily in the next lesson, but that's huge. Okay, what else did you say?
Also, if you look at a table, it has two sets of differences.
Did you look at a table?
No.
So is that a claim that you can make based on what you did?
Okay. No, but it's a claim I can make based on a quadratic.
Beautiful. Like, and I agree with you, right? Like, we know it's quadratic, so if we look at the sets of differences, we know that the first set of differences has what rate of change?
Positive. I'm sorry, it has negative.
Linear, right? Isn't the rate of change for a quadratic linear?
Yes.
Oh, yeah.
And then the second set of differences is where it becomes constant. The only thing I want to push on, I want you to remember, is if you're going to make a claim, you have to have checked it out. Just like your x-intercepts. You made a claim, did that one quite work out?
No.
No. Peyton did great deductive reasoning, though, based on the fact that, hey, I know it's quadratic, so I know it's going to have those two sets of differences. All right, was there anything else you said, Peyton?
Yeah, on the parabola specifically, I noticed the concave up and the concave down pattern. If you have, when both your intercepts are positive, then it's concave up. When both your intercepts are negative, it's concave up. But when one is positive and one is negative, then it's concave down.
Okay, so let's examine that. I like that claim. So when both intercepts are positive or negative, then concave up.
Yes. But if you have one positive and one negative, then it's concave down.
When one is positive and one negative, concave down.
And I'm not writing these down because this is all of literally what I wrote.
Okay? So let's test this theory. All right, we got this right here. So notice my y-intercept right now is -2. And now my y-intercept is -5. So I have two y-intercepts that are negative, and is Peyton correct that it's concave up? Yeah?
Yes.
Okay. So let me do this. Uh-oh. Wait. Now I have a y-intercept that's positive and a y-intercept that's negative which you said it should be concave down now?
Yeah,
Is that concave down?
No, it's not.
No,
Oh.
they did that yesterday.
Huh. Yes, what you got, Shelby?
It's not your intercept, it's your slope. So when one slope is negative, then it will concave down.
Oh, okay, so right now my slope for g of x is negative, and this slope is negative,
Which means
and it is concave
Oh.
up. And so by Shelby's theory, if it's negative and positive, it's concave down? Oh. Is that what we see? One is positive, one is negative, it is concave down?
Wow, so.
If they're both positive, then it should be concave up. Is that what we see?
Yep.
Okay, so let's come back to that in a second. And I think that's what you did yesterday, and I think you just wrote down the wrong thing.
Yeah.
But that's a great hypothesis. But notice that's what we want to test, right? So when both, not intercepts, when both slopes are positive or negative, then concave up. When one is positive and one is negative, that's concave down. We good?
Yep.
Okay? Anybody else have anything else to add?
Nah.
Shelby, I think I gave you, I was putting you up to say any extra details. Was there anything else you found?
Yes, for the y-intercept, all you have to do is multiply the y-intercept of f of x and g of x, and that gives you it for r.
So multiply the y-intercepts of f of x and g of x to get y-intercept of r of x. Why would it make sense that we're just going to multiply those y-intercepts?
Well, because for the sum you added, for the difference you subtracted, products multiplication, then you multiply.
Okay, right? Sum we added, difference we subtracted, product we multiplied. Is there anyone I have not gotten involved yet? Because I had Devin slated for quotient. So we've all gotten the chance to say something?
Yep.
Alright, so who wants to give us some information about what we're seeing when we see a quotient of two linear functions? What kind of function is that?
Nothing we understand.
Yeah, how do you know that?
Because we
Look
don't
at
know.
It's a
Because
rational.
look at it. Say it again.
It's a rational.
It's irrational because you and I talked about that yesterday, so we're going to discuss that in a second. But have we seen a function
No.
that has two different pieces to it?
Actually, we have.
You
with
told me that's the
relative-
same line.
Oh yeah.
No.
How?
I said it's one function, but it is... Okay, your question is how is that the same function?
How?
Yeah.
You said it was the same line.
It's not the same... Well, first off, is it a line?
No, well, the same, like it connects.
I never said it connects.
Oh, I'm about to say.
Well, I understood it that way.
Okay, so that's a good thing to ask, right? It's not that they connect. That was creepy. We got Casper trying to get up in here. We're not playing like that. Okay,
Let's learn some math.
so notice what are we doing when it's a quotient? We are
Actually,
dividing.
you
Okay?
did touch on that last year when we were going over relative minimum and relative maximum. We were trying to do the recursive and explicit for it.
I think you might be mixing something up because I'll go ahead and tell you. I would never punish a Algebra 1 student with trying to figure this out. We just haven't learned this math. It's not terrible math. You just haven't learned
No,
about
it's
this.
terrible.
No, I mean, you
It's not
showed us
terrible.
a few of these. Like, I don't know what
Okay,
they
I
are.
might have shown you a few of these. But, so, I want you to look right here, Shelby. So notice how this is a quotient. First off, I want you to notice, does that look like an exponential that has a variable in the exponent?
No, but it does have relative minimums and maximums.
Hold on to that thought for a second. Does that look like a linear, which is y equals mx plus b?
No.
No. Does it look like a quadratic, which has a second degree to it?
No.
No, right? So that looks nothing like what we've seen in the past. Now, Corell, you did mention that it's rational, right? Right? So, what is this called?
Ratio.
A ratio. You can also write a ratio like a fraction, 2 to 3. And that's why fractions are also called rational numbers. Hey, what do I have right here?
Rational numbers.
Well, a rational
Function.
function, right? It's a ratio of one function to another. You see how that's the division between two different functions? It's a ratio between those two functions. Now, the reason, Shelby, that there are two different pieces like this is, if I substitute a foreign, and not foreign as in a word like for, F-O-U-R, into this equation, so K of 4, so that would be 2 minus 10 divided by 1 minus 1. Can I divide by 0? It's impossible, right? That does not exist. And so if you notice right here, you look closely, there's a line right there at x equals 4 that I do not touch, do not cross, but I can substitute any number to the left of it, and I can substitute any number into the right of it, and so because I'm plugging an x value in, I'm getting a y value out. It never touches, these two pieces never touch, but it is one single function. It's just stuff around that 4. It's okay, you haven't studied it yet. You will once you've learned other aspects of functions. Just like anything new, you're like, man, that's weird. Yeah, that's cool. Okay, so quotient is like nothing we've studied before. That's all you need to know for now. Alright, really quickly, I want to look at a couple of ideas. First off, we've already talked about the idea that we're going to add our slopes, add our y-intercepts, subtract them, multiply them. But this is a lot of information, and you can memorize it. I don't encourage it though. All of this information should make a lot of sense. If you look at the top of this task, I don't know where my blank copy went, it does say algebraically what makes a quadratic function. Well, when I look at the sum here, right now I have f of x equals 3x minus 3. I have g of x equals negative 4x. I think that was a negative 2. Yep, minus 2. In order to calculate that h of x, what am I doing with f of x and g of x? I'm adding them. So Desiree, what can I substitute in for f of x for this particular set of information? And Layla, what can I substitute in for g of x? Now, I'm adding those two functions. What is 3x minus 4x? So was Peyton correct that we're just going to add those additive rates of change? Yeah, 100%. And notice the power is still to the first, which is a linear function. What is negative 3 plus a negative 2? So we still have a linear function if we look at the algebra. You should probably make a note of that. The same thing will work out with a difference that we're just going to add to linear, subtract to linear, and so we'll still get a linear function with an additive rate of change. But when I look here at a product, okay, so in this problem I have, so r of x is equal to f of x times g of x. And this f of x is equal to x minus 2. And g of x is equal to x plus 1.5. So what am I going to do with f of x and g of x? Don't everyone answer at once. What am I going to do with f of x and g of x to get r of x?
I said we're gonna ask
for a product?
Oh, we're gonna add.
What's a product, Corel? Say it again, Desiree. Multiply. What do we do with f of x and g of x? It's right here. Multiply. Does anyone recognize this idea of a binomial being multiplied by a binomial? Should look super familiar.
Nope, not at all.
Not at all, right? The homework of 6.3, that ready section, what do I need to do here?
Distribute out.
So x needs to be multiplied by x plus 1.5. That negative 2 needs to be multiplied by
The x and 1.5. Where you end up.
I want you to notice x times x is x
to the second.
Wait, so what type of function is this?
Quadratic.
Quadratic. X times 1.5 is plus 1.5x. Negative 2 times x, negative 2x. What's negative 2 times 1.5? Actually, I'll just give that to you. I'm not sweating that. What I want you to notice is, the reason I'm bringing this up, that was my y-intercept, right? This is my y-intercept, right? Gave me a negative 3. Hey, what's this y-intercept? Negative 3, right? You can try to memorize all of this, but all of this makes sense when you look at the algebraic representations. The algebra explains these ideas. All right?
I heard.
Good. That means you're having to think.
I knew you talking.
Last detail I want to point out. So remember how Peyton originally and then Shelby added on was talking about the slopes, right? When they're both positive or both negative, it's concave up, right? Well, when I do a positive times a positive, it gives me a positive. If this was a negative x times a negative x, it would still be a positive x squared, right? But what if it was a negative x, or a positive x times a negative x? It's going to be a negative x squared. So when it's positive for that leading term, it's concave up. When it's negative, it's concave
Down
down.
like a frown.
There you go. All right. Mr. Lippman is going to pick up at this point
Mr. Who?
and get you started.
Mr. Looking.
How dare you, acting like you don't know this man. He's been trying to help you all the time.
That's my favorite teacher. Yeah,
Mhm.
Mr. Lippman can teach. Yes, sir, Mr.
He's
Lippman.
not a teacher. He's
He's teaching now.
almost a teacher.
I actually am about to officially be a teacher.
He is a, I mean, he's passed all his
I have a job
certifications.
now.
No, I just
He has a
wanted
job.
to- I just
So,
wanted to-
we're gonna jump into
This is-
6.4, which is what Mr.
Oh,
Katie's
yeah, we
handing
got a
right
rabbit
now.
Rabbit, rabbit.
So we're gonna work on this for the rest of today and then all of class tomorrow. So we're still representing these quadratic functions with our different representations, so table, graph, algebraically. But we're also gonna talk about, some of the details of those quadratic functions, like domain, range, increasing and decreasing. We'll get to those details later, but this is what we're gonna be looking at for 6.4. We're also gonna keep looking at these SMPs. We're gonna keep reasoning abstractly and quantitatively, as well as looking for and making use of structure, which is pretty much that whole conversation we just had was all about looking for and making use of structure. So we're gonna keep using those skills, but for today, we're gonna be looking at 6.4. Now we're gonna do it a little different, is we're gonna do a group assessment on 6.4. So what that means is that you and your group will be working together on this task. We not only wanna see kind of like what y'all know about this information, but also how well y'all can work together and collaborate. So that will also be a part of this. We wanna see y'all collaborating, as well as how much information you've retained from some of the lessons. But you're free to use Desmos calculators. You can use all the previous tasks. So the notes we just took, Gold Rush, iRule, all those tasks we've done in the last like two or so weeks. Like you can use any of those notes, any of that work. But this task is centered around the situation where Misha has a new rabbit that she named Wascal. I still am not used to that name. I've been saying that.
I'm with you.
She wants to build a pen so that the rabbit has space to move around safely. Misha purchased a 72-foot roll of fencing to build a rectangular pen. So for this first question, it's going to ask what are the different possible dimensions. So we want at least like 3 to 5 possible dimensions. So don't write just like 1 and then move on. So we want like 3 to 5 possible dimensions of this rectangle. But this is the situation this whole task is centered around. So we're looking at dimensions, we're looking at possible areas, stuff like that. So do we have any questions on this task before we work on it for the rest of today and then tomorrow?
I think the name may be Wascal.
Wascal.
So the reason we said Wascal is because there's a mathematician whose last name was Pascal.
That was his last name?
Mhm.
No, what's his first name? You know?
I'm pretty sure it's his
No,
last
that's him.
name. I'm gonna look it up
I have
now.
no idea.
Wascal.
Where's King?
But if we have no other questions, go ahead and start working with your group, and we'll work on it for the rest of class.
Alright, so